Two, one.
Good morning, everyone, and welcome to our weekly seminar. My name is Alex Hills. I'm a member of the Engineering Advisory Board. But we have a great speaker today. He's a student of my colleague, Professor Haidari, who I've known for 18 years now. But Gus Lewis, I only met him 5 minutes ago, and already I like him. I like him for a few reasons. One is he's a hardcore Alaskan. He's a commercial fisherman, right, Gus? And secondly, he's an electrical engineer, so I like him right there. And the third thing that's really cool is he's figured out how to combine these two things, right? So the name of Gus's talk is Analysis and Pursuit of Small Vessel Electrification in Alaska, combining electrical engineering and the Alaska lifestyle. Who can argue with that? Gus Lewis.
Morning. My name is Philip Lewis, or Gus, but I often go by after the now late Robert Duvall and Lonesome Dove. So just a brief project introduction or presentation overview. I will go over my own who I am. I'll go over the project intro, get into what's taken up most of the time over the last year and a half in the shipboard microgrid modeling. We'll dive into the economic relevance and move forward into the mariculture industry and then steps over the last 6 months here. So kind of like Professor Hill already dove into, coming out of high school, I really thought I wanted to be a wildlife biologist. And then after speaking with people in Fish and Game, I realized I was going to need an advanced degree for that. I said, there's no way I'm ever doing anything beyond a bachelor's. So I moved to what I thought was going to be a terminal bachelor degree in electrical engineering. Loved my time as an undergrad. Got to the end of it, thought, I could probably do a little bit more. Professor Monk set me up with Professor Haidari. Somehow I coerced him into taking me on. Yeah, so now I'm here a year and a half later. But I fished all my life. I'm a pretty ignorant fly fisherman. I've also fished commercially for the better part of the last 10, 15 years. So enough about me. The project we've been working on, again, the first 3 bullets are really what's taken up the bulk of our time in developing a shipboard microgrid model representative of the commercial fishery industry, both in Alaska and then in other parts of the world. We want to focus on 3 primary components in the model, both vessel movement. We want to make sure the vessel moves as we intended to. We want to make sure the propulsion load is accurate, likewise its hydraulics load. Similarly, we validate the model against data which we previously collected of a 58-foot purse seiner in Southeast Alaska. After that, I will dive into what are some of the economic arguments for battery energy storage systems in Alaska's commercial fishing industry. We do a brief analysis on a 49-foot longline vessel. And then the last 2 bullet points kind of go hand in hand. We start looking at what are the other possible sectors for electrification, both in Alaska's mariculture industry, which you look at those loads, and then identify potential areas for electrification in that sector, and then I'll finally conclude with work. So just to give some background, development of the shipboard microgrid models, I should probably just go forth and explain that, a shipboard microgrid isn't that much different from an islanded microgrid, at least in conception. It is an islanded grid with one or more distributed energy resources. The development of these models really started 10, 15 years ago with steady state power flow optimizations for larger vessels in the maritime industry, things like cruise ships, cargo ships, passenger ferries. I know ferries have gone pretty popular in some Scandinavian countries. And then after that, they started moving into these real-time models to observe sudden load transients and see how the resources on board, especially electric drives, interact with one another, which is amazing. It's phenomenal research, but typically the papers on real-time analysis are often limited to, like I said, larger vessels, cruise, naval, cargo, you name it. And these vessels are typically equipped with a plethora of diesel generator sets. They similarly authors most often assume these pretty large, smoothly varying, predictable propulsion loads. They don't entertain much outside of that, besides maybe the occasional valve thruster. But what we're trying to emphasize is the loads emphasized in these bodies of work are not incredibly relatable to the fishing practices, especially in the commercial industry and in Alaska alike. Furthermore, hydraulic loads, which are such a pivotal piece of commercial fishing, are almost totally absent from existing bodies. So it was a big point of emphasis to integrate hydraulic loads. But beyond that, what's going on in Alaska, I know Chandler Kemp's not here, but a lot of the work in the fishing industry is focused on developing these empirical models from energy audits in hope of other commercial fishermen looking at these equations to use for their own advantage to size battery storage if they were hoping to integrate it on board their own vessel. But usually this is in the case of some hybrid electric drive rather than purely electric drive, so they're using a diesel engine. I mean, there's a plethora of different ways you can develop and drive, but it's usually a diesel engine and a battery with the occasional auxiliary diesel generator set. So again, more review, kind of like what I touched on last slide. This is really what the bulk of the industry looks like right now. It's a standard diesel combustion engine paired with a propeller, which is direct coupled. You have an alternator used for the household loads, hydraulic pump for deck equipment. And then if the vessel, which not all do, uses refrigerated seawater as opposed to just purchasing next to the dock, they will usually use an auxiliary diesel gen set since it's a pretty significant sea load. Our proposal, what we're shifting towards is an electric drive. We use a diesel generator set, so we are coupling a generator at the output of that diesel engine. We're using a battery energy storage system with both either a grid forming or grid following converter. We tie in the AC hotel loads, cabin lights, refrigerators, radar, satellite, things like that. And then we move into the drive itself, in which we're pulling off two motors, one for the propeller and one for the hydraulic system. And then they are both electric motors, and then the hydraulic will then send displaced fluid towards the hydraulic pump. So in our real-time analysis, we use Type of Hill. It's a real-time part of the loop simulation platform. There's, in the last 5 years, I know a really huge uptick in both utilities and private companies using this. Excuse me, not SpaceX, what is the Tesla uses it to test their own drive components for their vehicles. It allows you to monitor transients in real time under a changing load rather than something like simulating where you're witnessing waveforms in like nanoseconds or even greater extension period of time. And then, so the other thing that ties in, we develop our schematic or our drive in a schematic editor, and then I have control in a SCADA panel over what load I'm inducing and things of that nature. But really the benefit of doing this is rather than testing components in factory and then shipping them, which can both be expensive and time consuming, we can modify the model, over the course of 15 minutes and then test it rather than spend a whole lot of time developing a physical model. Again, so like I said, there's three primary components we're looking at validating with the model: how the vessel moves through the water, the load of both the hydraulic and the propeller. So the first set of equations we're kind of going to run through real fast is vessel movement. On the right-hand side, the figure is just data we collected. I don't think it's actually for this vessel that we tuned it to, but just kind of a general trend of how we do things. So the three governing equations we look at is the speed at which the vessel travels over time, which will be a quotient of the thrust developed or thrust delivered to the propeller minus the resistive forces acting on the hull of the vessel, and then that's all divided by the mass. And then we similarly have thrust dp. I don't have a table. I thought it was just over things. So thrust is a product of a non-dimensional coefficient for thrust, kt, the density of seawater, the propeller speed and arc rotations per second, or revolutions per second, propeller diameter. And then the hull resistance, we've simplified it to half of a coefficient for total resistance experienced by the hull, again multiplied by seawater density, vessel speed, and then the wetted surface area of the vessel. So that's dependent on the length, the beam, and then how low in the water. The draft is what you call it, but which is pretty much a perpendicular distance between the water line of the vessel and the bottom of the hull. The pain in modeling this is that CT, coefficient for hull resistance. So it's broken up into a wide range of resistances experienced by the vessel, air resistance, frictional resistance, and the big one is wave making resistance. We don't actually incorporate wave making resistance into our model just because difficulty in doing so. A lot of times what, especially like the Navy will do, the Navy will construct like this really proportionate small scale model. And I should first explain what wave making resistance is, obviously. Wave making resistance, if you've ever been up on a boat, they'll say getting up on step. And what it is it's pretty much climbing over your own wake. So as the vessel moves through the water, you'll notice that as you try to get up on plane, there's about a 30-second period where the vessel has to climb out of its own wake, essentially, to cruise efficiently. And that's what that is. And the other, so what the Navy does and other authors and researchers can do is they'll design a really small scale model of the vessel, push it through some body of water, and then see how waves are generated around it, and then they'll just step it up for the real vessel. We don't do that, and part of the reasons for that is one, the difficulty in doing so, and then two, more importantly, is for larger vessels, displacement vessels like long liners or cruise ships, or excuse me, not cruise ships, seiners, they're usually not traveling fast enough to begin with to where wave making is a huge factor. And then secondly, if you're a smaller vessel like a skiff, you're usually not traveling in your own wave. So you're not traveling when that resistance is super high because you're just going to be draining gas. So we kind of dropped that resistance term and focus on frictional air. But what we do in tuning is we plug in first for both thrust and resistance. What we're going to do is, based on the data we've collected, we're going to assume a couple points are at steady state in terms of vessel velocity. So we're going to get rid of that derivative, and then if we multiply that mass zero, obviously, and we can then derive our non-dimensional coefficient of thrust. And that's, again, what we need to input into our model so the vessel knows at what speed it's going based on the motor speed or propeller speed. So what we'll do is we'll end up doing this for a whole bunch of data points, and we're going to get a range of values for our KT, and then in the model, it's going to look at what the speed of the propeller shaft is. It's going to interpolate to see what KT value it should be operating at, and then it's going to pass that to the propeller. We do a similar thing for the load torque. It's a little bit easier because there's not as many moving parts. Now we have torque is equal to a non-dimensionless coefficient for torque, seawater density, again, propeller speed and RPS, and the propeller diameter. We rearrange for that dimensionless coefficient. One of the variables we measured in the sea trial is torque, so that's the value we have. So again, we're going to interpolate based on speed in the model what that value should be. And then lastly, in our control, we use a field-oriented control scheme. It's not super complicated. I won't spend too much time explaining it, but essentially your load torque from equations 1 and 2 are going to be, I don't have them posted here, but at the output of our motor, it's going to look in our model, what is our current load based on our speed. It's going to look at the difference between that is what the current torque being output by the motor is. Take that difference, send it back, use equation 3, what our shaft speed is going to be. If our load obviously increases, our mechanical speed is going to drop. It's going to derive some IAQ and ID axis current references to bump that torque back up. We'll pass those references through to PIs, generate an internal inverter reference for the voltage, and then finally pass that through a transform to get 3-phase equivalence. Okay, so the results from this, we've converted load torque into power at the shaft. For all intents and purposes, the values we get are close enough to where we can accurately model this vessel, both in terms of what the power is, the speed, velocity it's going through the water. You can see at some of the high end speeds, we start to deviate a little bit, but for the most part, we're operating between 500 and 1200 RPM. And again, you see a little bit of deviation, but we're not in that range. And a lot of times, we're just trying to get a ballpark estimate to see how our resources interact under changing loads. So on those two fronts, the model's accurate. The other big load we're looking at, we take a pretty conventional definition for hydraulics. Again, I never once played with hydraulics. I had a problem with hydraulics when I was in undergrad for like general physics. So this had to be taught kind of on as we went, but now Q stands for flow rate through the valves. So from the pump, we see you have some end value of the rotational speed of the pump in RPM, and then the displacement of the pump. Then we take our volumetric efficiency, which is at NP, and as a function of P, and kind of in your head, you can think, well, if a pump is displacing fluid, you can kind of track, and these are what these two graphs are showing. First for the hydraulic pump, and then the bottom one for the motor. You can think, well, if you're operating at a higher pressure, you're going to see more leakage through your pipes. So you're not going to displace quite as much fluid to the motor. So that's what that volumetric efficiency is we're taking it. And on the right-hand side of that equation is the equivalent for the motor. And we're just saying that displacement of the flow rate through your hydraulic circuit has to be the same as what's being produced by the pump and what is being delivered to the motor. And then the way we do it in the model is we define some hydraulic load that's acting on the output of your circuit. And then based on what speed you're operating your hydraulic motor at, it'll determine what your pressure has to be. So it's kind of difficult to come up with some linear relationship like as we did previously with load torque, because pressure will kind of just be what it needs to be to make ends meet in terms of what your load is. So on the left-hand side, you can see some of the measurements we had taken for a hydraulic. Actually, this vessel had two hydraulic circuits. This is for the larger one. So depending on how significant of a load you're operating on deck, you might have one or multiple hydraulic circuits. So this was for one of the two circuits. What we do is we induce a load on the left-hand side. You can see a load. And then again, your hydraulic power is going to be a function of what flow rate you're passing through your valves and what your operating pressure is. So kind of in the back, you can think of that, like that faded background as what your theoretical limits are for your system. And then what we're doing is we're making sure that our pressures line up. This pressure is one thing we're measuring for the vessel. And you can see, I mean, we don't have quite as much noise going on because I'm just going through and I'm doing this like one step at a time, make sure things line up. But for a load of about 30 to 35 kilowatts at a rotational pump speed of 1000 RPM, we're within reasonable means in terms of pressure. So we're operating about where we should be in terms of validating. Again, one of the things I touched on, so the last three slides were just showing that we can tune our model depending on data we collect on a per vessel basis. If we have data, we can tune it to make the model representative of any single vessel, not just the one we did it for. One of the other things I touched on at the very beginning was most bodies of research currently, especially for larger vessels, they're usually equipped with a plethora of diesel generator sets, and inverters are typically treated as some auxiliary piece of equipment for intermittent peak shaving or power sharing. They're not designed to be the backbone of that shipboard microgrid. In our case, where we're using either a combination of strictly an inverter, we have to put a little bit more effort into fine-tuning its parameters to make sure it operates as designed. Obviously, inverters aren't inertial-based systems like diesel generator sets. So what we do is we play with the droop, which effectively mimics how an inertial-based generator would slow or speed up depending on the load. And what we do is we kind of just went through a range of droop coefficients to make sure to maintain a steady voltage and or prevent against significant voltage and frequency sag under a changing load. So on the top there, we're just imposing some propulsion load, a pretty rampant step, and then making sure that our frequency and voltage don't sag beyond. I think the threshold was like 3% is what we were looking at. So we usually went with 2 lower values for each. The end product of this is you get some virtual test beds. So you can kind of think of this as like a typical operating condition, albeit this is over the course of 7 or 8 minutes rather than 10 to 15 days. But you have a vessel that goes out, takes steps out of the harbor, gets to its fishing grounds, turns on its hydraulics, reels in gear, turns them off, goes back to the fishing grounds. And in doing that, this is kind of a snapshot of what we can monitor in real time. We're seeing how the waveforms interact between components, whether you're trying to prevent against faults or you're doing a significant fault analysis. But you can see here, again, it's kind of tough to visualize because it's just one snapshot, there's nothing changing. But we're inducing some load top. You see the output from the generator set in waveforms B and C. The current waveform C, you can kind of imagine goes along with D as you're within the drive as that inverter shifts between the positive and negative rails of the DC link. You're going to see kind of those spikes in the current being supplied to the drive. And then your final plot E is just the 3-phase current being supplied to the motor. All right, so that's really what's taking up most of the time. That paper is under 2nd review. So we're kind of waiting to see what happens to that, but we're hopeful. But when we talk about this, really the outside motivation, especially locally, when you talk to fishermen, is they're curious, if you were to install battery storage on your vessel, is that going to produce long-term savings? Because obviously you're not purchasing fuel at the dock. Depending on where you're operating, like you have camps in Bristol Bay and on Alaska, it's just incredibly varied. You don't know what the cost per pound of fish is going to be. Typically, the further off the grid you get, as in Alaska or Bristol Bay, the fuel prices at the dock are going to be pretty significant. So that's their own personal interest. If you were to replace diesel with batteries, are you going to see savings? And beyond that, one of the things is diesel is just not a super efficient source. I mean, relative to other forms of fuel, it is. But engines are typically designed to operate within over a wide. They're operating most efficiently over this wide range that's designed between 25 and 100% of its fractional load. But typically with these large vessels, when they're hauling in gear and fish, their propulsion load like non-existent, and the only load they're running are these hydraulic loads. And if you have a diesel generator or a diesel engine rated for 250 horsepower or whatever it is, and you're pulling in deck equipment that's only consuming 5 horsepower, you're operating at an incredibly inefficient range for that engine. And so, I mean, just per the graph, you're operating under a fractional load of, say, 10%, usually for over 75% of the time when you're fishing. So your diesel use is poor. That conversion rate is even worse. So the outside motivation is, can we get rid of that inefficiency? Batteries obviously have a lower operation maintenance cost. And then one of the other things which is kind of surprising me, but not terribly, is a lot of times I'm not trying to let the cat out of the bag here, but not always are batteries going to be a super economical choice. But if it is a point where it's close or at least competitive with diesel or any form of gasoline, operators will often go with it anyway, or they're at least feel compelled to go with it, because when they're selling product, they can advertise that they're a clean operation, yada, yada, yada. It improves their story. All right, so for this kind of brief analysis, we looked at a 49-foot long line vessel. And kind of like I said, you see, I can't even remember really what the engine was rated for. I think it was, internal horsepower, not kilowatts. This was data we had collected previously, just some steady state points. So long lining, which is really what I've done in Prince William Sound for a handful of years, is you go out, You deploy a line that could be, up to a mile long in some cases. You attach weights, you sink that line down to the bottom of the ocean floor. You have these hooks that are arranged every 5 to 15 feet, and you're targeting like groundwater or ground fish, halibut, cod, rockfish. You let that line soak, you reel it back in with the hydraulic gear. So for this vessel, it had a transit speed of 36 kilowatts. Again, when it's fishing, it was just under kilowatt up. And then the transit load was 0, or the hydraulic load while in transit was 0. Fishing was 3. The reason we went with a long line vessel is typically vessels aren't quite as large as purse seiners. The hydraulic loads are relatively low compared to other fisheries. We just thought from the jump, if batteries were going to be competitive, they're probably going to be most competitive on the long line vessel. No. So what we did is we looked at comparison for this vessel. If you're better off using diesel, we went with the generator set in this case for an electric drive, 430 kilowatt hours battery storage, which would be a purely battery operation, and then 172 kilowatt hours, which would be in a hybrid electric drive. We looked over 10 years at a pretty moderate interest rate, and assuming diesel cost $5 per gallon. We looked at 3 different spots. Of course, this doesn't factor in PCE, but it gives you kind of a view across a range of electric import costs, whether batteries are going to be competitive across the state, depending on that price. We looked really at the 3 primary values we looked at was the net present value over those 10 years, which is just if you were to take all the costs over that 10-year period, see this lump sum on day 1, that's the value, or how much debt would that be? We looked at the equivalent uniform cost, which would be that net present value, and equivalent cost over each year of that 10 years. And we looked at the levelized cost of electricity, or energy, excuse me. You kind of see right off the bat, diesel is still going to be your best bet. And that's not to say that batteries are poor choice, or that they won't become more favorable in the long run as you have, whether that battery cost comes down or salvage values go up if they have second life applications. But they're not an amazing fit with larger vessels in Alaska. They're spending 10 to 14 or even sometimes more days away from harbor, because the amount of volume of battery storage you would need to be able to travel for 10, 15 days. The capital cost affiliated with that is just usually too significant for an operator to overcome. So the thing they could do is they could always go out for a shorter day. They can go out 2 to 3 days, come back, replenish, go back out. But in the period where you only have so many days you can be fishing, you're going to be hard pressed telling an operator, well, you're going to have to change it to make our research significant. And they're probably just going to give you a one-finger salute. Anyway, that was just a brief study we looked at, presented that in Connecticut last fall. So kind of what we had to do is we had to shift gears and say, all right, well, for larger vessels in Alaska, you're going to be hard pressed to find someone who's willing to put up that amount of capital for batteries. So what other operations are there in the state that are more predictable, don't require as much of an investment, and that are really cycling their batteries with more frequency? And we found that one primary one that we're looking at right now is the mariculture industry, and that would be like kelp and oyster farmers around the state. They're going out, they have a farm site that's 2 or 3 miles from the harbor. They're not going to be like traveling around chasing fish. They're going to the site. A lot of times they just turn the engine off, or they're skiffs, so they're just turning their outboard off, plucking or doing whatever they're going to do at this farm site, come back. So it's a predictable practice. Don't need nearly as much storage. You're cycling your batteries frequently. And then kind of similarly to that, and we haven't gotten too much into it, but in a dream scenario, if you have enough time, The set net industry is another one that would be doing a relatively similar thing. So set netting is you're fishing from a bank, like at the mouth of the Casilla or the Kenai or Bristol Bay. They have a ton of camps, and they're running 2 to 3 skiffs. They have these nets they're setting up perpendicular to the salmon channels. They run the skiff out 2 to 3 times a day. They pluck the net, they come back, and then they do that over the course of 4 to 6 weeks. So again, you're cycling your battery frequently. You know how far you're going. There's not a whole lot of variation like there is for larger fisheries. But again, because these are skiff operations, it's not, at least for our intents and purposes, more interested to look at the entire industry rather than just electrifying a skiff, because there's typically not as many loads. Some skiffs are these aluminum boats that are like 18 to 20 feet in length. They have started equipping these skiffs, depending on the application, with hydraulic rollers, but most of them are not possessed with those. So we want to look at, on a community scale, say there's 10 kelp sites, how should they be harvesting kelp or whatever they're farming? And then more so over the last year and a half, since we've been doing site visits and monitoring how these, what's the word for it? God, I'm blanking. How are they processing kelp? How are these processors dealing with what they're taking in? And a lot of times, unlike with fishing, these large commercial fisheries across the state, which have really set in stone processing methods, and these huge commercial processors, a lot of these farmers are doing them themselves. So they're going to either an independent contractor to process kelp for them, or they're doing it by their own means, which they're not typically used to. They're used to dropping off the load of salmon, having the buyer there, they bring it up the crane, they go back out. Now they're kind of having to do that themselves because it's not a huge industry yet. And what we're trying to give them is some platform or guideline to save them money in the long term. So again, I'm kind of being a bit redundant here, but if we look into the mariculture industry, kind of like I said, this isn't for any specific vessel, but this load profile, the relative frequencies in terms of trips, like how much energy is that skiff consuming per trip it goes out to its farm site and comes back. So like, if you remember a few slides ago when we were doing that analysis on that 49-foot long liner, to make it a fully electric or fully battery electric drive over the course of, I think we looked at like 5 to 10 days, it was going to require like 430 kilowatt hours of storage. In this case, we're looking at, you can probably get away with a 50 kilowatt hour battery. You're going to have to sacrifice some trips on the high end, but that's obviously a significant drop in capital. And again, the loads are less significant. You can implement an electric outboard. A lot of this is redundant. Again, what I'm trying to drive home for is it's far more predictable practice and far more feasible for a smaller operation that's going a predictable distance than a vessel that's out in Prince William Sound chasing fish for 14 days. So what this is, I have to talk about this on Monday to a bunch of farmers. So we're going to give it a test run now. What this is looking at is the economic impact. So we're looking at we over a 15-year period are trying to project life cycle costs for operating a 250 horsepower gasoline outboard with an electric alternative that has 50 kilowatt hours of battery storage. And what we're trying to drive home is this vertical line, or not vertical line, but this black line here shows what point do you start saving money? At what point do you achieve payback and then start seeing savings? And we can project based on what we've seen for quotes is that the installation cost for an electric outboard, regardless of the horsepower, is going to fall somewhere between $500 and $1,200 in installation cost. So that's one thing we're varying. And then the other thing we're varying is gasoline usage. How much fuel are you purchasing on a year-to-year basis? So a lot of times you're not going to know this exactly. So a better way to look at it is in terms of how many trips you make. So for a kelp farmer, if we went with, say you install this 50 kilowatt hour battery at an installation cost of $750. So we're offering, you would have to be taking 120 trips a year to break even or start saving money. And a lot of times for the kelp industry, they're on that, they're starting to strat or get close to that point. And again, that's where we've seen people in the past that still go for it because the public perception of their operation. With oyster farmers, they are doing trips up to 3-4 times a week for the entire year. So they're far more likely to see achieve payback and then see significant savings. So that's whereas with the long line vessel, it wasn't even close. Diesel was still a pretty favorable choice. We're trying to show with skiff operations, you're far more likely to achieve payback. It's a far more favorable practice for electrification. But again, that's not enough to write any sort of paper on, just to go off. It's what we're doing right now is looking at a community scale. If you have 10 people who are all going back and forth to their farm sites, how will that impact the grid? And we're looking at a whole bunch of different processing methods. So I think this is the last slide. In summary, what we did, the bulk of the work over the last year and a half has been developing that shipboard model. We did a pretty significant transient analysis on it. We looked at inverter integration. Still waiting on the final review for that to come back. Kind of in the midst of all that, we did a brief conference paper on the economic impact for large fishery like longliner. Discuss the challenges of achieving payback for a fully battery electric vessel. And then from that, we start to piggyback in a different direction towards skip operations, whether it's a mariculture farm or if it's a set net camp. And then that last bullet, kind of like I said, we're moving towards a community scale optimization. Yeah, that's a wrap. So I'm happy to take questions. I'm sure I'm jargoning through a whole bunch of that.
Gus, I mean, I've had you for so many classes and I've learned 2 things I didn't know, that your name's Philip.
Oh yeah.
And you're an avid fisherman.
Yeah, it's a pretty unhealthy addiction. It's about this time of year I start getting pretty twitchy. So
I actually had a question about your previous slide, which kind of showed the profitability. So I mean, do you anticipate that line shifting as efficiencies kind of start to creep in with
at the what cities?
efficiencies with electric?
Oh, efficiencies. Yeah, so we factor that in. I mean, I don't think the electric efficiencies for like round trip battery efficiency and then your inverter efficiency are both around 90. You might see a little bit of impact with that, but I think the bigger thing is, again, how frequently you're making trips to your site or whatever you're doing. And
I mean, are there other costs that are coming down?
yeah, so like one of other costs coming down, like in terms of
Batteries,
battery-
cheap.
yeah, so like I think one of the things that would really make batteries more attractive is second life applications. Like, what are you, when you after their 15-year life cycle cost, are you able to sell your battery for any sort of profit? And I know a lot of actually John can talk more about this than I can. A lot of homeowners, I think, are getting batteries with second life applications or something of that nature, where rather than buying a battery new for their own home, they're buying a recycled battery. So there's that operation and maintenance cost. The problem with O&M, which we don't fully factor in, if you're fishing in somewhere like Bristol Bay, it's unlikely you've got someone on site that can deal with the battery. You see the same problem with like electric vehicles off in Kotzebue. Like, they're great for what they do, but if it breaks down, like, you're kind of in a heap of trouble. You're going to have to ship it back to Anchorage. So in theory, the cost is lower, but that probably doesn't factor in shipping. But I really think with this plot specifically, what we're trying to say is it comes down to how often you're cycling the battery. And then also I think for this one, we assumed a fuel price of like $4. So, you know, in some places like Bristol Bay or King Salmon or wherever you're at, if that fuel cost of the dock is exceptionally higher, you're up for closer to $5 a gallon. You might see it shift down a little bit, but on the battery side, I at least presently construct, I don't think you see a whole lot of shifting.
So in terms of kilowatt per hour costs, diesel versus electrical, like a kilowatt of diesel versus kilowatt of electrical, pretty significant difference.
It's a bit of a difference. Malcolm and I talked about this yesterday. I don't want to come out and say that batteries are not going to work, given that that's what we've done for the last year and a half. What I'm saying is it's a little, it depends on what you're using batteries for. It's really what it comes down to. Diesel's probably going to be more competitive in larger operations. But if you're okay sacrificing distance or variability or something along that lines, you can make electric incredibly attractive. But yeah, diesel's still a strong option.
I think you said you submitted a paper that was on the long line story.
That one was just a conference paper. That one, yeah, so the work that was on that 49-foot long liner, which we analyzed different combinations of battery storage, that one was for a conference. The other paper that's under the second waiver review was for the shipboard microgrid modeling, which is a bit more extensive. And
So you're still waiting for an answer?
yeah, we just submitted that. Well, we just submitted it the second time. No, we've just addressed the second round of revisions, so now we're waiting on the yes or no. But we're pretty hopeful.
And I had a question about the economic analysis for the long liner. That's several slides back where you had a tape it, right. So there you're giving the net present value of buying fuel for 10 years, is that?
So we're looking at, I have a table that I could have included. So the things we're looking at the capital cost affiliated, the variable O&M per year, the fixed O&M per year, we're looking at fuel costs per year, and then that electricity.
So what did you assume about the life of the equipment?
We looked over a 10-year period. I don't know if for a long line you're going to cycle the battery. I think most marine batteries you can cycle or do a full cycle 4,000 times is usually what their lifetime is.
Right.
We assume 10 years.
So you assumed 10-year life.
Yeah, we assume that, and that's not to say that I think that it will probably go beyond that, if not double. Just to keep things relatively simple.
So what are the last two columns there then?
So the equivalent uniform annual cost is taking that net present value.
I didn't get the acronyms.
Yeah.
What about the last one?
Levelized cost of.
Oh, okay. And so what would be the numbers for diesel?
So diesel is that top one. So rather than do a diesel engine, we went with a.
That's the.
Yeah, so this is the baseline here. This is what we're projecting for a diesel operation. It's probably going to be over a 10-year period, $113,000, or on an annual basis, about a $15,000 investment per year. And in your most attractive electric case, you're going to be about $4,000 over that threshold. So again, the biggest factor with these larger vessels is you can make batteries more attractive if you're doing more frequent trips and you're coming back, offloading product, recharging, going back out. But
And one other quick question, when you did the equivalent annual cost, you must have assumed the discount rate for that?
yeah, I think I said that I think it was 5%, and then we did compounded monthly, so I think the effective was 5.
You're gonna have a degree in finance too.
Yeah, well, this is all pretty basic. I'm sure if there's an economist in here, I'd be getting yelled at for the shortcuts, but
I think you did okay.
okay, that's great. That's great.
Yeah, I have a degree in finance. You're fine.
Oh yeah, I forgot about that.
You're good.
Yeah, extensive financial background.
Well, you're.
Yeah, so.
Question on the, to say for the battery cycling, so this is assuming that these ships are going back to a charging station.
Yeah, so that's one of the other things. There's a handful of assumptions we're making. They do supply, I can't remember what the exact voltage is at most harbors across the state. It does make the assumption that they are coming back and able to recharge at the site or at the harbor and go back out. I think in June, not Juneau, excuse me, Stewart's actually developing, it's not a far-fetched assumption, Stewart is developing a secondary dock for their own cruise ships. I think they hold 2 cruise ships at a time. They come in, they shut their diesel and generator sets off, they import from the electricity, so they're importing from, you don't know if that's gas or HEA.
A big plug-in.
They're plugging into the grid. So it's not a crazy stretch to say, if you ever wanted to extend your transmission to the local harbor. But yeah, I mean, there are plenty of hybrid drives across the state right now. And they are capable of pressure. And they're charging. So it just depends on how long you need to sit in the harbor and recharge. Given that the fishing load is small, 1 kilowatt, 3 kilowatts, is there a scenario that is worth modeling with a battery that is smaller, has smaller energy capacity? Yeah, so we do, so on the shipboard side, I guess even to just go off this slide. So one of them, we're assuming the first scenario we entertain is you're still running diesel. The second scenario we entertain is you're purely battery electric. And then the third scenario, which is really what's being rolled out today, is a combination of 2. And that's usually what people are doing. So what they do, at least if you're operating a large vessel, they're usually going with a hybrid drive. They use a diesel engine to get themselves out to operate their heavy loads. And then when I had mentioned, rather than run their diesel engine inefficiently, they use their batteries that are usually either pulling off the diesel engine to recharge while in transit, or more often they're using a smaller auxiliary diesel genset to keep that battery charged. So again, I don't know if that answers the question, but that is definitely a scenario that we try to implement, and that most people are implementing if they are moving toward batteries.
Another question on, I don't know if there's anything to go with this, but like the size, the volume of diesel you need in these size ships versus the weight of the batteries themselves, is there any substantial difference?
A lot of people ask that. A lot of people are concerned about the weight of the batteries, and what we've discussed and then decided is that the physical volume of, I mean, if you were to go with 430,
Yeah,
430, whatever it is, the physical volume that those batteries would require is a more significant limiting factor than the weight of batteries. So I would imagine it's kind of like if you're running your diesel tanks, a similar thing.
but it's not like a detrimental thing. So like, this is too much weight for the boat or too little weight for the boat?
I mean, I'm sure I haven't done too much analysis on what that sweet spot is for the boat. I know I just listened to a presentation last week for a guy that was incorporating batteries into his own gillnet vessel. And they had to do some reconstruction of the underneath the boat to make sure the batteries had a place to sit. And they had to insulate that room properly or beyond what it was previously. But from what I've listened to, people far smarter than me have talked about housing batteries, it's not a significant burden.
What about the internals of batteries? Because over time, we've been changing from, alkaline lead acid batteries to all these different new ones. Which ones were you guys assuming?
Most of the marine batteries we looked at were lithium iron phosphate batteries. And I think most of the batteries that have been implemented in the Southeast are the same. I may have heard of one that used lead acid, but I can't recall exactly. But
Is there any new technology coming up that's even more?
Fuel cells are attractive for a lot of people, kind of for the reasons I'm stating, whereas you're not having to store energy, rather fuel cells can produce it itself, power itself. We went with batteries in our case because it's a readily available technology. And that's what most people are moving towards. But I think, especially for larger vessels like longliners or seiners, who don't want to make repeated trips back to harbor to refuel or recharge, if they can get their hands on a fuel cell, regardless of what they're using for a fuel, whether it's hydrogen or whatnot, that's probably going to be more attractive. But getting your hands on hydrogen in Whittier is not. I don't know when that's going to happen, but I think that tech is a far more feasible option than batteries would be in a lot of cases. But we kind of designed that microgrid model that we developed. What we really try to emphasize more so is the capability of the inverter itself. It doesn't really matter what you power the inverter with. It could be a fuel cell. For our case, we went with battery just because I think it's easier for readers to conceptualize because there's so many electric batteries already in production. But we try to place greater emphasis in our writing on the inverter itself and how that interacted with the diesel generator.
Okay, so you talked about that in your vessel, you are like in a hybrid operation, as you say, you are using diesel genset and battery altogether. So can you tell more about it? Maybe how does it work?
So the couple scenarios we ran, there's so many different drives. So I could have put a slide here that just talked about the different drive systems on these vessels. So like I said, today most people are using direct drive. You just have a diesel engine powering or a mechanical coupled to your propeller. The other one that's typically being installed today are hybrid drives. They're not purely electric because there's no generator attached to the engine. So you have a diesel engine and a battery that's powered by an auxiliary generator set. And there's some equipment, I don't even remember what exactly it's called, so I'm not going to try, that shifts between what source you're pulling from. We went with a hybrid electric and a battery electric. So what we have is we have a diesel engine powering an electric generator, which then supplies the load, and we have a battery that's also supplying the load. So we're fully electric. Where is it? Electric operation. The only thing we're varying across our research in this paper is whether the inverter is operating. Is it in grid forming mode, or is it in grid falling? Like, is it assisting the diesel generator set during certain periods? Or is it taking the brunt of the work? I don't know if that's exactly what you were asking.
Like from this figure, I can see that diesel genset and base are like working together like at the same time.
Yeah, so I think the four scenarios we have is we had in our paper, we have a diesel generator set operating exclusively. We have a battery inverter operating exclusively. Then we have a diesel generator operating as your grid forming, and a diesel gen or a battery inverter as your following source.
Okay, so diesel in GFM and base in GFL.
GFL, correct? Yeah.
Like, just I'm curious, did you run both of these like in GFM altogether?
At no point, we did run one scenario, which was kind of in that ballpark where we used diesel generator set to get us to the fishing grounds, and then we roll that back and turn on the inverter. And now the inverter is acting in GFM while we're operating hydraulic equipment, and then we shut the battery down, start the diesel back up, and as your GFM source to get us back to the harbor. But at no point do we have both of them operating simultaneously in GFM.
Okay. Thank you.
Yeah, no worries.
No more questions? One more question?
Yeah, I got another question online there.
Solid state batteries, if manufacturing challenges are overcome, will provide higher energy density and lower fire risk. I'm not actually sure. Donut. I imagine that's a manufacturer. Lab finished production of solid state batteries. Yeah, so I mean, I think there's a handful of marine batteries that would be applicable. We didn't spend a whole lot of time, digging to see what the advantages of each battery type are. We went with what is typically being rolled out for marine applications. But yeah, I know fire risk is obviously a big deal, if you're having them, because you could definitely be screwed.
All right, and the password for today's survey is pursuit, all lowercase. Thank you again.
I exchanged texts with Kimberly last night. And it's Ilcon is already in what